Welcome everybody on this webcast about a detailed rigid body cervical spine model based on inverse dynamics. My name is Mark and I will try to guide you through this presentation. First I would like to introduce you who is behind. My name is, as I said, Mark and I will present. Arne Kies, he will host this webcast and will help by making everything all right here. And then we have Søren Christensen, who will be part of the panelists, and he will be available for answering questions during the presentation. During the presentation and also after the presentation, it will be possible to ask questions. And the way you do it is if you push on the right bottom of the screen on the question mark, and then type your question in the question answer panel. And it's important that you send the question to both the host, the presenter, and the panelists. So in this case, everybody will be able to see the question. And if it's possible to answer the question during the presentation, then Søren will do that. Otherwise, we'll keep the question after the presentation, and then I will try to answer the questions. And also after the presentations, I will be available for answering questions. So once again, please answer questions during and after the presentation. So, very short about me. I'm affiliated with the Department of Mechanical Engineering at Aalborg University, and I'm also affiliated at the Department of Health Science and Technology, a center which is called the Center for Sensory Motor Interaction, also at Aalborg University here in Denmark. The work I will present today here is a cooperation between the Center for Sensory Motor Interaction and the Department of Mechanical Engineering. From the Center for Sensory Motor Interaction, I work together with Deborah Vella and Dario Farina. And from the Department of Mechanical Engineering, we work together with John Rasmussen. And I have to acknowledge those people because they have also done a large part of the work. Obviously, this screen is for the people who cannot hear me. So quite often we have problems with people not having sound anyway. So I'll wait for a couple of moments and then we'll continue with the presentation. All right, I got a message I can go on now. So the cervical spine is a very complicated structure. And it's a very dynamic structure which acts to support the head on the trunk and orient the head in space and transmit forces. And the head is relatively heavy. It's about 4 or 5 kilograms, and it's balancing on this relatively small base, which is the neck. It's a very complicated biomechanical system with many degrees of freedom about each joint. And we have many muscles, at least 20 pairs of muscles around the neck. And they are necessary in order to balance all these degrees of freedom. Moreover, the system is highly redundant, meaning that specific forces and specific movements can be produced with several combinations of muscle actions. Neck pain is also a very interesting problem in society, and it's significant because we can see that the frequency of people with neck pain is actually beginning to match the proportions of low back pain. And probably this has something to do with the increasingly sedentary lifestyles, lots of office work and computer work. Also, we have seen in the literature that when people have neck pain, we see changes in motor control. And this has been documented in people with chronic neck pain. So an important point is that we believe that in order to be able to understand how the development of discomfort and neck pain is taking place, we need to quantify the loading of the muscles and the loading of the structures in the cervical spine for different working postures and movements. So this is a kind of the background why we have done this work. So what we want in this case is we would like to develop a general detailed cervical spine model which is able to predict muscle and the reaction forces in the cervical spine for a given movement or posture. Moreover, we would like to have that it is relatively easy to share this model, so that other groups will have the possibility to download the model and improve the model and try to validate the model for their own purposes. So this is the kind of the general aim we have. So now I will go in more detail about the cervical spine model, how we have built it. We have built it in the antibody modeling system, and what's probably most of you know, it's based on inverse dynamics and optimization principles. So we use the optimization principle to solve the muscle recruitment problem. Moreover, it also means that this model is not really suitable for explosive movements of very unexpected movement like whiplash situations. But it's more, we can use it in more controlled situations like in ergonomic design or in ergonomic research or pain research. Lots of the data described in the model is based on a PhD thesis by Marika van der Horst. She did this a couple of years ago at the University of Eindhoven in the Netherlands in cooperation with TNO. And if you're interested in her work, you can download it from this webpage here. And after the presentation, we will send this presentation out as a PDF file to all the participants, so you can write down this. It's not necessary to write down this webpage here. So, kind of the basic model is based on, is built of 9 rigid segments. We have the head, we have the 7 vertebrae of the neck, and we have the thoracic part. And then the joints are quite special in the neck. Between the T1 and C2, we have 3 degrees of freedom cervical joints, which kind of mimics the movement degrees of freedom possibilities we have in that part of the neck. The upper 2 joints are kind of a special design in the neck. Between C1 and C2, we have a 1 degree of freedom universal joint, which is for rotation. So in the case you rotate the head, so most of the movement takes actually place between C1 and C2. The other one is between C1 and the head, which is also a universal joint, but with the axis in a different direction for extension flexion. So in extension and flexion, most of the movement in the neck takes place between the head and C1. The center of rotations is an important parameter in the model, because that basically defines the moment arms of the different muscles around the neck. And that's based on work of Amewo et al. In 91, which was, I think, co-written by Bogdak from Australia. And then we have really many muscles around the neck, and most of the muscles are divided in muscle fascicles. I will not go through all these 136 muscles, of course, but I will mention a few in order so you get an idea about the complexity of the model. So we have the flexor muscles here. Some of the flexor muscles here we have in this drawing here. We have here very close to the vertebra. We have the longus colli and the longus capitis. They are very close to the vertebra of the neck. And then we have a kind of lumped hyoid muscle. An important muscle is also the sternomastoid, which is a muscle which you can see very clear from the surface of the neck. And it's this one here, and it's important both in flexion but also in rotation of the neck. Somewhat deeper, we have the so-called scalenus muscle, and they are divided in anterior part, a medial part, and a posterior part, a medius part and a posterior part. They're located here. And we have a quick look at the back side of the cervical spine. And again, I have not listed all the muscles here because then you would actually not be able to see anything. But I have some of the muscles here, the multivitus, cervicus, small muscles here, important for stabilizing the neck. And we have a more general muscle here, the semispinalis capitis, here, which is also important for flexion of the neck. And I have listed some others. We have the longissimus capitis and the semispinalis cervicus. So, and many more in the neck model. Also, the trapezius is part of the neck model, and some of the shoulder muscles, like the levator scapula, is also part of the neck model. Just to remind you that it is okay to ask questions during the presentation, and Søren will try to answer that. But you can also wait after the presentation. But again, you can ask questions if you like to do that. So this was a kind of description of the neck model. As I said, I have not mentioned all the muscles in the model because that will take too much time and it will be too boring. But now I will talk about some validation. And as you all know, it's really important that it's been done, but it's a big challenge, especially when you have so many parameters as we have in this model. So what we did as a very first approach is that we compared the maximal force generation capacity of the cervical spine model and the transverse plane with data from the literature. So I'll explain how we did that. So first we defined an input in the model. Because, as I said, this model is based on inverse dynamics, so you have to define the movement and you have to define the external forces. In this case, we have defined the posture of the neck in a kind of anatomical positions, and we keep it that way. And then we have a horizontal force vector, which was imposed on the head, and it was rotating 360 degrees about the vertical axis. So I have here 4 of the situations here. Let's start with this one here. We have this blue vector here, which is the force vector working on the head. And this force vector is pointing to the right. So that basically means that the muscles on the left side have to be active to balance this external force. In this case here, we have a force vector pointing backwards. So that means the external force is pointing backwards. That means that the muscles in front of the neck here have to be active in order to balance this force. Well, and here we have the force pointing to the left, so the muscles on the right side have to be active. And here we have the force pointing to the front, and you can clearly see that the muscles here on the back have to be active in order to balance this external force. So if you do that, and you analyze that, can you make a polar plot? And it looks like this. So this is a kind of a model of the force generation capacity of the model. So this position here, that is the front position, and this is backwards. So here have we flexion, we have the lateral flexion to the left, lateral flexion to the right, and we have extension. And the blue line here indicates the maximal force generation capacity for that direction. So for extension, that's about 226 Newton. For right and left, it's 145 Newton. The model is perfectly symmetric. So then, of course, the numbers of the lateral flexion to the right and the left will be the same. And then the flexion, the maximal flexion of the model is 41 Newton. So if we compare this to the numbers in the literature, we can come to the following conclusion, that from the model, the maximal extension and the lateral flexion forces, they are quite consistent with values reported in the literature. The maximal flexion force is within the range you can find in the literature, which goes from 40 to about 150 newtons. So that's a huge range in the maximal flexion force. So one could say that ours is in a low end, so maybe we have to do something about that. But it's still within the range you can find in the literature. So then we have done some more thorough validations, and at least we have started to do that at Aalborg University. And we're still in a pilot phase. We have done some pilot tests. So we use here a device here where you can put the head in and clamp the head, and then we can measure the forces in frontal and extension flexion directions. There are some strain gauge transducers around here. We can measure the forces in the lateral flexion direction and also in rotation. So in this case, you can have a quite complete idea of which forces you're producing by the neck muscles. In this pilot experiment, we did several things. We did some maximal flexions, voluntary flexions, and also some ramp ups and ramp downs of different directions. And we measured on 4 muscles by wire electrodes. So we measured, here you can see, we measured by wire electrodes the sternomastoid muscle, the sternocleidomastoid muscle on both the right and the left side, which is a flexor muscle and important for rotations. And we also measured on the back of the head, around here, we measured the splenius capitis muscle, which is an extensor muscle, also by wire electrodes both on the left and the right side. So here are some preliminary results for a case we called isometric rotation, because we were trying rotating the head, but the head kept in place in a kind of anatomical position. And we asked the subject to start at a low level at isometric force and then ramp up to a certain level and then ramp down again. It was a submaximal isometric contraction, so we didn't reach the max here. Here on the vertical axis, you have the activity in percentage. So 0 is no activity in the muscle and 100 is the maximal activity. Here on the top 2 panels, we have the sternocleidomastoid on the right and the left side. And in the down panels, we have the splenius capitis on the right and the left side. The red line is the activity estimated by anybody, and the blue line is the processed EMG data during these contractions. The first thing you can see that the trends predicted by anybody are the same. So the sternocleidomastoid on the left side has a higher activity, predicted activity, than the predicted activity on the left side. So this one is lower than this one here. And that's also what you can see in the EMG data. The absolute values are somewhat different, quite different here, as you can see. And that's something which can have several reasons. But the trends are looking quite good. The same about the trends you can see about the splenius capitis. The splenius capitis on the right side is predicted active here, and also the EMG has a clear activation. The splenius capitis on the left side is predicted to be 0 by anybody, and there is a very small activity in the EMG value, so it is also pretty close. Then another example is the isometric lateral flexion. In this case to the right, and also the rotation was actually a rotation to the right. I forgot to say that. So here again, the trends, they look quite good. We have here the red line again is the activation predicted by anybody. The blue lines are the activations, the measured EMG activations. And here the trend again, you can see the estimated activity and the measured activity are looking quite right and compared to the left side. There is still Again, the left side we see in the EMG values, we see small activations, and the predicted activity is totally zero. So as you can see, this is the start of the validation. We will continue that, and then we'll try to measure more muscles as well, because we have only 4 muscles here, which is not probably not totally representative of all the muscles we have in the neck. So the next part of this presentation will be about application of the neck model, where we try to predict the neuromuscular adaptation of experimentally induced neck pain using this model I just presented. So I will give you an introduction about the problem here. Again, I want to say that neck pain is indeed a significant problem in society. And given the complexity of the cervical spine, it is expected that alterations in afferent feedback, so pain from the muscles, for example due to pain, will induce modifications in the cervical motor control. And this has indeed been shown by people with chronic neck pain. So what we are interested in, several questions. What are the changes in muscle function in the cervical region when you have muscle pain? And what are the mechanisms underlying these changes? And the last questions is then the most interesting for me, is can musculoskeletal models help us to answer these questions? So that's kind of the background why we did this research. There are some hypotheses about influences on pain and control strategies. So this is some kind of an official circle here with the arrows here in the 2 directions. So let's start here. If you have pain, that can lead to different control strategies. It can also be the other way around. If you have kind of a control strategy which is can lead to pain. If you do that, the change control strategy can change the muscle properties, maybe the muscular force, but also the electrical parameters within the muscle. And change the muscle properties can again change the way we experience pain. Also the pain itself can change the muscle properties. So some of these relationships have been proven, and some of these relationships are still hypothetical. So what we do is that we assume the muscle properties to be constant, and then we only look at the relationship between the control strategy, the motor control, and pain. And people have done that quite a lot in experimental situations. And what they have done, they have given injections to people who don't have any pain complaints with hypertonic saline. And this hypertonic saline gives, which is a model for muscle pain. And in that case, you can assume that indeed the muscle properties will stay constant, and then we can study the control strategies. So this has been done, for example, by Deborah Valla and co-workers, which is recently published in the Journal of Applied Physiology. What she did was to inject the right sternocleidomastoid muscle with this hypertonic saline, while asking the subject to produce a flexion force, an increasing flexion force. So in this upper panel, you have the EMGs of the sternocleidomastoid, and on the lower panel, you have the EMGs of the splenius capitis. The blue is kind of the baseline, where there's no pain, and the orange one is the EMG values where there is pain. So let's first take this one here, which is the muscle which was injected by this hypertonic saline. And there's a very clear inhibition of the EMG. So the EMG values are much lower in the presence of pain, And you should remember that the mechanical output, so the force, was the same as before in the two situations. So the painful muscle is clearly inhibited. But also the muscle on the other side, the contralateral muscle, the sternomastoid muscle, was also inhibited, was lower, while there was no injection in that muscle. And if you look then at the splanus capitis on the side where there was an injection, but not in that muscle, there also we see a clear inhibition of the EMG activity. And also on the contralateral side, there was an inhibition of that muscle in the presence of pain in the right sternomastoid. So it is kind of this situation we would like to mimic in the model, and then see if we can tell something more about the mechanisms behind it. So what we do, we have the model again, and we put a constant force of 30 Newton, external force on the forehead. So this has to be compensated by flexion forces of the muscles. However, it turns out when I do it in this situation, there was no co-contraction of the sternomastoid and the splanus capitis when you have this pure flexion force. However, in reality, in the experimental situation, there was a clear co-contraction between these two muscles. So what we did was the following. So and we could see when we had this external force, a little bit offline, a little bit from the center. Then there was a co-contraction, predicted co-contraction in the model. So we have in one situation we have the external force a little bit to the left, and in the second we have the external force a little bit to the right, and then we took the average of these two situations. In this case, we try to mimic the kind of stability which seems to be necessary in the neck for this external force, because in reality you will never have this pure flexion force in perpendicular to the head. There will also always be some changes in direction when doing this. So now we'll go through the calculation scheme, how we try to mimic this the pain in a normal condition. So first, the normal condition. So we have our model, the cervical spine model, which I have presented. Then there is the input in the model, which is the movement. In this case, there is no movement. We keep the model in neutral position. There's no velocity, there's no acceleration, and we have the external force of 30 Newton. From this, the redundant equilibrium equations are formed, and then we solve the equilibrium by optimization. And as output, we have the muscle forces and the activities which are necessary to balance this external force of 30 Newton. What we then did, the predicted force in the right sternomastoid, the muscle we want to kind of virtual inject with hypertonic saline, this predicted force we take as output, and we multiply that by 0.06. So we take the force, 60% of the force in a non-painful condition. This force was then imposed as an external force on the model instead of the muscle. So we removed the right sternomastoid, but we have an external force with exactly the same line of action of this right sternomastoid, but with 60% of the force which was estimated before in a non-painful condition. And this 60% comes from the EMG values, where we could see there was roughly an inhibition of 40% in the right sternomastoid muscle in the case of the injection with hypertonic saline. So now we have a cervical spine model in pain, one could say. Again, we have the redundant equilibrium equations, and then we estimate the muscle forces and the activities of the rest of the muscle, which in that case we could say we kind of calculate the adaptation of the muscle force and activities while there is pain in his right sternomastoid muscle. So these are the results here. So we have the blue bars or the EMG or the predicted activity by the model in the no pain condition, and the orange one will be the predicted activities in the painful condition. So here we have the ipsilateral side, and the sternomastoid on the right side. There's already this orange bar here, and this one here is forced. So this is not estimated, but this one here is forced. But the rest will be calculated by the model. So then here are the models, are the results, and we see in all the muscles, in the ipsilateral side of the splenius capitis, we see an inhibition, a predicted inhibition in the painful condition, and also in the sternomastoid side, muscle on the contralateral side, we see an inhibition in the vertebral pain condition, and also the splenius capitis, we see an inhibition, a predicted inhibition, I should say. So it seems that the simulation predicted an inhibition in the synergistic contralateral sternomastoid, and also in the antagonist splenius capitis on both ipsilateral and the contralateral side, which we also saw in the experiments. This might suggest that our central nervous system counteracts the inhibition of the painful muscle by choosing a muscle recruitment, still following the strategy which minimizes fatigue. This statement we have to investigate more for other situations as well. Of course, we have some main assumptions in this case here. The main assumption here was that we forced only the painful muscle to be less active in the simulation, and the rest of the muscles were then predicted by the model. But in reality, when you inject the person with a hypertonic saline injection in the sternomastoid muscle, this causes a quite large area of so-called referred pain, which is kind of which you can see in the drawing, which also was from this article in the Journal of Applied Physiology. So here we have injection site, but there is actually some pain areas far away from the injection site. So it might actually also be that also these areas of referred pain might cause some inhibition, but we need further research to see if it's really the case. In conclusion, I hope I've showed you that musculoskeletal models, and especially the cervical spine models and the principles of biomechanics, can help us to understand the change in muscle coordination. Because I think this is important, because a lot of the pain research in the cervical spine area which is going on is based on experimental research, and it's very difficult to predict by hand or by intuition which muscles should be active and which muscles are necessary for a certain kind of movement, because we have so many degrees of freedom. And I think in this case, the numeric model of the cervical spine could really help us. It also means that we can quantify the change in muscle loading in painful conditions, and also the loading of the structures around the cervical spine. The future developments are that this model will become available here in the autumn in the public repository. As already said, we did some pilot validation experiments with wire electrodes, but we're planning to do more detailed validation experiments, because now we have 4 muscles on. I think they look promising. Also, a plan more for the far future is that we want to include the fissure joints in the model, and especially in the more extreme cases when we go to the ends of the range of movement, fissure joints might play an important part in the force distribution of the cervical spine. Well, thank you very much so far for your attention. I would like to acknowledge the sponsors of this neck model, RBM and AP Furniture, and we have some websites here available for more information. Yes, and now it's time for questions. And now I have to look at Arne, the host, see if there are any questions.